Hi, everyone. So great to see people again. Some out in Scotland, or maybe not in Scotland. Benjamin, good to see you. Great to see everyone. It's really great to have everybody here today. This is our first seminar of the new year, and lots of people from our previous year since the launch of the seminar series last fall. And we're excited about a new year. For those of you who haven't met me before, I'm Jillian Hadfield, director of the Schwartz Reisman Institute for Technology and Society. And this is our weekly event to connect people across disciplines and fields around issues of technology and society. So we really aim for a really rich interdisciplinary conversation and lots of conversation. So we're going to, normally our goal is to have 45 minutes of presentation and 45 minutes of discussion. And Roger's asked, I think, her to do part one and then maybe do 15 minutes of conversation and discussion. And then he'll do the last part and we'll do the last 30 minutes at the end. You're welcome to ask questions in the chat. I'll keep track of that. And Roger, do you mind being interrupted along the way? You want to wait until the question?
Yeah, that's fine.
Okay, so I'll keep track of that, and you can we'll also use if you want to raise your hand. That's good too. Okay, I also want to introduce somebody new to our community. It's our SRA's new postdoc, Beatrice Magistro, who will be co-hosting some of these sessions. Beatrice's research explores how technology and automation are changing governance and politics, and how citizens respond to automation-related economic disruption. So welcome to our group, Beatrice. Very glad to have you with us. And now, my pleasure to introduce our first speaker of the new term, Roger Grosse. Roger is an assistant professor in the Department of Computer Science here at the UT and a founding member of the Vector Institute. Roger was a postdoc at Toronto as well, after having received his PhD at MIT, studying under Bill Freeman and Josh Tenenbaum. And before that, he did his undergraduate degree in symbolic systems and master's in computer science at Stanford University. But we did not overlap at that point. I met Roger very early in my odyssey of learning about AI and AI safety. And he was also a founding member of the AI safety discussion group, I think, at Vector that we now collaborate on. Roger's research interests focus on machine learning, especially deep learning and Bayesian modeling. And he works on developing algorithms that train faster, generalize better, give calibrated uncertainty, and uncover the structure underlying a problem. All really important things. Furthermore, he's also investigating the important problem of ensuring that AI systems remain aligned with human values. And of course, that's a core goal of our work here at SRI. Roger is going to talk today on how can deep learning research inform long-term AI safety. So we're starting the semester off with the big picture questions. I'm really looking forward to that. Okay, Roger, let's kick it off. Thanks.
Thank you, Jillian. So I'm Roger Grosse, and I'll be talking about how deep learning research can inform long-term AI safety. And so by long-term AI safety, I'm referring to the field that asks the question, if we were to build a very powerful AI system, how can we ensure that it continues to act in our interests? And so in this talk, what I'll try to do is outline how we think about AI safety and how deep learning research can fill in some of our conceptual gaps. This won't be an exhaustive talk. This is not like an exhaustive list of all the ways I think deep learning can help. Just a couple areas where I think it's particularly useful. And so I'll begin by giving a very quick overview of some of the background assumptions behind what I'll talk about. And then I'll cover two areas where I think deep learning has something to offer. The first is forecasting AI timelines. And the second is Mesa Optimization, where an algorithm might itself build another optimization algorithm with a different objective. And so this talk isn't original research. It's almost entirely summarizing work done by other people. I'll have maybe a couple tidbits from my own research. And I'll mostly be raising questions rather than giving answers. So don't be disappointed if you don't walk away with answers. So I'll begin by giving a brief overview of why we should be concerned about human-level AI and superintelligence. And I'll mostly be summarizing arguments from this book, Superintelligence, Paths, Dangerous Strategies by Nick Bostrom, because I think this book did such a good job of outlining the strategic space and what different assumptions you might have about AI safety and what would follow from them. So for the next few slides, I'll mostly be summarizing his claims. So an artificial general intelligence, or AGI, refers to a still hypothetical artificial agent that's capable of doing pretty much any intellectual task that a human can. But the worry is that it wouldn't necessarily stop at human level AI, because it appears that both human brains and current computers are very, very far away from the physical limits of computation. And so it appears that it could be physically possible to build machines that are not just human level, but actually super intelligent in the sense of being vastly more intelligent than humans in pretty much all relevant domains. And this could mean machines that think like humans, except maybe thousands of times faster, or it could mean machines that think at a qualitatively higher level, the way that we think at a qualitatively higher level than chimpanzees. And so the argument is that if we were to build such super intelligent machines, then we'd no longer be the most intelligent agents on Earth, and we'd no longer necessarily be in control. And so the reason to be especially concerned about superintelligence is that there are reasons to think it might happen quickly. So in particular, recursive self-improvement refers to the process where AIs are responsible for most of their own development. So that's where most of the progress comes from, rather than from human researchers. And under some assumptions, this could lead to extremely fast rates of improvement in AI capabilities, also known as an intelligence explosion. And the reasons for this aren't terribly complicated. So an oversimplified model for thinking about it is, let's say that AI and human capabilities could be measured as a scalar, essentially depending on the speed of thought. And imagine that each increment of human time results in a fixed exponential increase in AI capability. So think essentially of Moore's law. Humans are the same as they were 20 years ago, and computers get faster, or computation gets cheaper at a very steady exponential rate. And so if the human contribution were the entire story, then the curve of technological progress would look something like the blue line in this figure. So the y-axis is a measure of AI capabilities on a log scale. And essentially, we have a Moore's law-like behavior where progress continues exponentially until it reaches the physical limits and things level off. But once we cross the line, right, so if this were to happen, there'd be some point at which AIs are essentially human level. And then 2 years later, they think twice as fast as humans. And then 2 years after that, they think 4 times as fast as humans, and so on. Right. And so that's what happens if only the human contribution counts. But if AIs are contributing to their own development, then once they're equally smart, then Moore's law will result in a doubling every 1 year instead of every 2 years. And then after that, it'll double in half a year instead of after 1 year, and so on. And so the rate of doubling will just keep speeding up until basically we have what looks like a phase transition to a much, much higher level of AI capability. So that's what's shown in the orange curve. And that's what is often referred to as a technological singularity. So just imagine decades or centuries worth of progress compressed into a very short period of time, like a few weeks. So why should we be worried about this? Well, there are a couple core theses that Nick Bostrom makes. The first one is to respond to this common misconception that as AIs become more intelligent, eventually they'll converge to more worthwhile goals. But this isn't necessarily true. And so he proposes this orthogonality thesis, which says basically that any level of intelligence is compatible with any goal. So you could have a very, very smart AI whose fundamental goal is to produce as many paperclips as possible. And no matter how smart it gets, it's not going to unlearn that goal. This is associated with the idea of utility maximizing agents. It doesn't necessarily require that, but that's sort of the easiest case to think about. And so those of you who do reinforcement learning, RL is basically a way of approximating sequential decision-making to maximize a cumulative reward over time. So that'd be a pretty clear instance of this. And there's a mathematical idealization of a super intelligent AI with arbitrary goals, which is AI XI. So it's something we can actually write down and reason about its behavior, even though it's uncomputable to actually implement. So the other main component of why we should be worried is known as the instrumental convergence thesis. So even though AIs could be designed with almost arbitrary goals, there's certain convergent sub-goals that they're likely to settle on. So regardless of what their terminal goals are, it's likely that they'll have an interest in self-preservation. Now, this isn't as obvious as it sounds, right? We think of self-preservation as being sort of built-in drive that we have, but the AI wouldn't necessarily care about survival for its own sake, but only as a means towards accomplishing its other goals. So the way Stuart Russell puts it is, you can't fetch the coffee if you're dead. The second goal that it would have is goal content integrity, right? So if we mess up and give it the wrong goals, then it'll have an interest in preventing us from changing them. It'll have an interest in acquiring lots of resources that it could use to do things. So for instance, if we built an AI with the goal of computing the digits of pi, then it might be useful for it to turn the entire world into one big data center so it can compute more digits. So a common misconception that AI researchers have when I talk to them about superintelligence is that maybe the whole theory depends on intelligence being a scalar, something that we could attach a quantity to like IQ. But that's not the case. So when we talk about intelligence in this context, it's basically an intellectual shorthand. Sort of like how if we're talking about evolution, we might describe evolution as trying to maximize fitness, even though that's not really biologically realistic, and we would sort of build more mechanistic arguments if we need to. So intelligence plays sort of the same role in these discussions. So Nick Bostrom lists some hypothetical cognitive superpowers that an AI could have, and a subset of these might be sufficient to bootstrap to the others. And what I think about this, I don't want to get political here, but I'll use the example of Donald Trump to make a very specific point, which is that Trump didn't have all of the skills and knowledge that other politicians had, but he had some unusual skills. He was a world-class entertainer. He could distract the media. He understood a certain segment of the population really well. And you wouldn't be able to put him on a political IQ scale necessarily, but the skills he did have were sufficient that he could take over a political party, win an election, get the nuclear launch codes. He had the entire talent and resources of the federal government at his disposal. So there are kind of a lot of different potential paths by which an AI could become very powerful. And I think the extent to which intelligence skills are generic versus task specific is still a big open question in our field. So what can we do about this? Well, there's the field of AI alignment, also known as the AI control problem, that basically tries to ensure that a superintelligence, if built, would act in our interests, or at least not cause catastrophic harm. And so one of the books to look for about this is Human Compatible by Stuart Russell. And I'm not going to talk in much detail about AI alignment techniques in this talk. It's a little bit tangential to this discussion. But basically, this is why why we should be thinking about AI timelines now, right? If the hard takeoff is actually possible, then our only hope is essentially to solve the AI alignment problem in advance, or maybe design AI architectures that aren't consequentialist and like don't have goals and desires and things like that. All right, so the first, that's all kind of setting up the context for what I'll talk about. The first main part of the talk is about forecasting. And if you think about other important global issues like climate change, here is a report from the Intergovernmental Panel on Climate Change, which summarizes the contributions of hundreds of researchers who are collecting data and analyzing it and building models and trying to form quantitative forecasts of how climate change might progress under different assumptions and different actions we might take. And unfortunately, we don't have anything equivalent for AI. We have a lot of people in the field making sarcastic tweets, and we have some individual people trying to make educated guesses about how things will turn out, but we don't really have a science of AI forecasting. And there are two questions that are especially important. The first one is how long until we get to human level AI? And the other question is, once we're at human level AI, then how rapidly will it become superhuman, right? Would we have an intelligence explosion? Or maybe under some other assumptions that wouldn't happen. And even though the question of whether AI is a human level is a little bit ambiguous, I think when you combine these questions, it won't be ambiguous, right? If superintelligence happens, we'll know it, the world will look completely different. It's not an ambiguous question. And so different assumptions about timelines would have different implications about how we should prepare. So if we believe in slow takeoff, right, if we believe that once we're at human level AI, it'll be another 50 years until we get to superintelligence, then we'll probably be okay, because the human institutions will be able to co-adapt with AGI and solve the problems as they come up. If it happens over the course of a few years, then we would have time to react in certain ways, right? There could be, the UN could get all the countries together and have like an international moratorium on AGI. There are also things we have to worry about, like international arms races, because there could be a significant first mover advantage. And if we could have very fast takeoff, like we get superintelligence in a matter of hours or days, then we probably wouldn't even notice until it's too late. And so the only way we can make things work out well is if we prepare far in advance. So what do the AI experts think? Well, here was a survey given to AI researchers who published in NeurIPS and ICML in 2015. And in the top right, they were asked to estimate distribution over when we get human level intelligence. And different people have wildly varying intuitions about the timelines. And so that's basically the individual black curves you see here. Some people think it'll happen in 10 years. Other people think that we'll never get there in this century. But in aggregate, people seem to assign about a 50% probability that it'll happen in the next 50 years. They also polled AI researchers on much more specific predictions, like when particular AI milestones will be achieved, when various careers will be automated. I think there's a little bit of AI chauvinism here. The AI researchers think that AI research will be the last job to be automated, even like long after mathematicians. I'm not sure I buy that. But generally, they're expecting major AI milestones to happen sometime in the next few decades. Very recently, Ajay Kotra built a more quantitative model trying to estimate AI timelines, and they tried to separately forecast different pieces of the puzzle. So how will hardware progress continue? How about algorithmic progress in AI? How much will resource investment in AI change? But the most difficult piece of the puzzle was the number of flops required to train what they call a transformative AI model, which you can think of as roughly equivalent to AGI. So that's the really hard part of the analysis. It's what she devoted most of the report to. But at the end of the day, she comes up with this distribution over the timelines. And the colors represent different modeling assumptions that go into it. But generally, it seems to be peaked in about a 20-year timeline with a significant tail. And so, so she built a detailed quantitative model of AI timelines, and it had a lot of uncertainty. So at the end of the day, there's just a very wide distribution over when we over the amount of computation required for AGI. But like, why should we expect this even to be a worthwhile thing to pursue, right? Why should we expect AI timelines to be at all predictable? And I think the reason for this is that AI scaling as a function of various kinds of resources has turned out to be really surprisingly regular. So it seems possible that we could actually come up with a much more precise model of AI progress. And so, for instance, one question you could ask about AI scaling is, how long does it take you to train a neural net to a given accuracy as a function of the amount of parallel computing capacity? So companies like Google are very interested in this question because they want to guide their investment in better forms of hardware. And so it turns out that this follows very regular scaling curves. So what we have on the left is a plot for a particular architecture and a particular task. This is a transformer language model. So the x-axis is the batch size. You can think about this as the amount of parallel computation available. And the y-axis is the number of steps that it takes to train the model to reach a given accuracy. Both axes are on a log scale. And the dashed line represents perfect linear scaling. So with twice the amount of parallel computation, you can train your model twice as fast. And what we see is that there's a linear regime, and then it levels off. So for small batch sizes, you get a linear improvement in efficiency with parallelism, but eventually it levels off. And this isn't just one model, but this seems to be a universal pattern that holds across many different architectures. So on the right, we have everything from convnets to recurrent neural networks to transformers, and they all have this characteristic pattern. Perhaps even more surprising is that these sorts of scaling laws also apply to really sophisticated architectures like GPT-3, which a lot of you have already played around with. So as you might know, GPT-3 is a kind of architecture that was trained on a very simple task, which is to predict a distribution over the next token in a sequence, which you can think of as the next word in a sentence, even though that's not strictly true. And it's turned out that despite the simplicity of the task I just described to you, GPT-3 can actually do surprisingly diverse things like creative writing. It can do simple arithmetic problems. It can write computer code. It can compose Celtic music. And so it's not something we would call human level AI, but the idea that like such a simple architecture supports complex behaviors, it may be evidence that intelligence is more generic than we previously thought. And so, if you look at the outputs of GPT-3, they often seem surprisingly inspired and creative. But when you measure the performance quantitatively, you get amazingly tight scaling laws. So in the right-hand figure, we have a plot of the performance metric of a trained model. And there's a particular way of measuring the performance, which is on a log scale. And on the x-axis, we're plotting the number of parameters in the model, also on a log scale. And what you get is a very precise power law fit that holds over multiple orders of magnitude. You can also do similar experiments for things like the size of the data set shown in the middle, and also for the training time that we see on the left. So the blue curves correspond to training runs for individual architectures. So it'll take a while to reach its kind of peak performance, and then it levels off. But then if you combine all these curves for different architectures, it traces out a very beautiful power law. And so these power laws are things that actually are able to extrapolate to much larger sizes than we're trained on. So these plots were generated from GPT-2, but then when they ran GPT-3, it actually fit very nicely on the same plots. And in fact, this is probably why they were willing to spend so much on training GPT-3, right? If they were spending multiple millions of dollars training a single neural net, they probably want to have a precise understanding of what benefit they'll gain from the resource expenditure. And one other surprising thing from this result is that the performance seemed to be surprisingly insensitive to the fine-grained architectural choices. So you could have one really wide layer in the network, or you could basically use the same number of parameters to construct a really deep network with, let's say, 10 layers. And it turns out that 2 layers works better than 1 layer with the same number of parameters. But beyond that, it doesn't seem to matter. So the rest of the curves here basically lie almost on top of each other. It doesn't matter if you're using 2 layers or more than 6 layers, it's the number of parameters that matters. And so I think there's a lot that we can learn through detailed quantitative analyses of neural net scaling. But there's a lot of work that remains to be done. So those scaling laws were for a particular task of sequence modeling. Do similar things happen in other settings like meta learning, reinforcement learning, some sort of game tree search, and so on? Can we get a more fine-grained understanding of why those laws happen? Like, is there something about the statistics of the number of close neighbors that appear in data sets of different sizes, things like that? To what extent can different sorts of resources like data and computation substitute to each other? And perhaps the most difficult one is how can we estimate the difficulty of what remains to be done, right? How can we put tasks that haven't been solved yet, like training a professional lawyer, on a difficulty scale so we can estimate the time to achieve them? So these are, I think, some of the open questions that deep learning can start to address. So this is it for part 1 of the talk. I'll open it up to a 15-minute discussion.
Okay. Thanks, Roger. Any questions to get us started? Or comments?
I apologize, I had a conflict for the first half hour, so this is a very uninformed question, but of the things that you have mentioned so far, I don't know, what's the one that you think is maybe not most important, but that we're like most poised to make some progress on?
Yeah, I mean, I think there's a lot of low-hanging fruit left to do in understanding the scaling laws. So as I say here, like understanding at a more fine-grained level, what are the reasons for them? If a network follows a particular scaling law, does that imply that it's effectively doing some sort of like non-parametric regression or nearest neighbors or things like that? So yeah, I think there's a lot still to be done there.
Roger, Reed, you have a question. Go ahead, Reed.
Hey, yeah, thanks. Yeah, I think this is, I think this sort of scaling of AI systems towards an AGI is really interesting. I just sort of was wondering, is this falsifiable? Like, you have sort of this implicit assumption that there will be some sort of AGI in the future. How would we, what if that isn't possible? Is there any sort of mechanism to detect that? And sort of following up on that, what if it doesn't look like people are imagining? What if it does exist, but isn't in sort of some framework that we can think of right now?
Yeah, great questions. So one hypothesis that I didn't really discuss is maybe AGI is just impossible, right? Maybe it's physically impossible to build an AGI. And I think this would be a very surprising result about physics, right? It could turn out that there's something very special about human brains that just can't be simulated on silicon-based architecture or anything else we're likely to be able to build. I would find that very surprising. I think most people would probably be very surprised by that. So I'm operating under the assumption that it's physically possible. It could be that there are big ideas required that we haven't found yet and that we're not going to find in the next 200 years, right? And I think this seemed very plausible maybe 10 years ago, right? If you're an AI researcher 10 years ago, you could probably write down a list of fundamental abilities that humans have that AIs didn't seem to have, and that we had no idea how we might be able to achieve, right? How can we sort of combine the reasoning ability of a search procedure with the flexibility of a machine learning system and things like that. By now, I think AIs have shown so many different kinds of abilities that it's hard to pinpoint individual fundamental skills that they're obviously missing. And it seems like a very plausible hypothesis at this point that everything is a matter of degree and scaling up existing architectures. But this could turn out to be an illusion. Right? It could turn out to be that there are fundamental components of intelligence that our AI systems just don't have, and that we're not going to be able to figure out in the next 100 years. And so I think that's what implicitly contributes to the very long AI timelines, the ones that are longer than 100 years.
Thanks, Roger. Benjamin.
Thanks. Yeah, I had a question going back to the sort of goals that might be emergent from any sort of, goal-oriented AI, like self-preservation. And one of them was not wanting to change its goals. And I was sort of curious about that one, about where that one comes from, because I sort of think I have most of these, but I don't think I have as a goal to prevent myself changing goals. I'm often quite open to, in the future, my goals might change, and that's fine. I'll just pursue different things. I don't want to lock myself into my present goal set, even if I could. So why would we think that that would be sort of something that they would naturally emerge from these systems?
Right. So humans aren't exactly consequentialist agents, right? I don't think that even in principle, you could write down a utility function that we're maximizing, right? Maybe we're carrying out certain biological drives, but everything isn't really driven by one utility function. And so this idea of goal content integrity basically comes from the idea of sequential decision-making to maximize utility. And I think the agent would realize that if someone kind of reaches into its software and changes the goal function, then it'll be doing something else other than optimizing that objective, and the value of that objective will be much lower than it would have if it continued to optimize it. And so a sequential decision-making agent would be incentivized to try to prevent anyone from interfering with its goals, to like prevent anyone from interfering with its goal definitions.
Great, thanks, Roger. Jack. You're on mute, but you want to come off mute there.
Is it my turn? Sorry.
There's, yeah, it is your turn. Yes, sorry.
Yeah. So I was intrigued by something you said earlier, because I've always been worried about the AI alignment framing, the AI alignment problem, for the reason that we haven't figured out, you know, the human alignment problem or the corporation alignment problem or the AI researcher alignment problem. So it seems like, you know, not likely to be a helpful way. It might be a helpful way to pose a problem, but not to solve it. But you suggested earlier that we might think of non-instrumental AI agents. So my question is, does thinking about like the progression of AI intelligence, or that's redundant, the progression of AI as a scaling in the ability to achieve, you know, the performance on these benchmarks kind of already assume an alignment problem framing of how AI is progressing?
Right. I mean, it's a very good point that there's no well-defined notion of human values. Different people can have competing objectives, and that's also something that we'd have to deal with as part of AI alignment. And so even leaving aside the kind of inherent challenges of AI alignment, there are also the usual challenges of any powerful technology. You have to worry about misuse. You have to worry about international arms race scenarios. And international arms races could also kind of interact with the safety issues, because then the groups developing the AIs could be incentivized to sacrifice safety in the interest of speed. And so certainly, like all these sort of social issues come up the way they would with any other technology. I don't know if that answered your question.
It was a vague question.
Well, let's put a pin in that. We can come back to it. Daniel.
Hi. Yeah, I just have like a quick question, I think, about the analogy that you made of like a super intelligence or AGI to humans and humans to chimps. And it seemed like you're talking a lot about doing things faster, but when I think of a chimp and a human isn't doing things that a chimp does faster. It's actually doing very different things. And it has like interests that are, you know, a chimp is not interested in playing Go. It just doesn't make any sense for it to even think about that. And so when we think about, or when you think about an AGI, are you thinking about something that only is going to get better at things that have human utility? Or is it something that's going to, in getting artificially generally intelligent, is it going to develop kind of like a set of goals, or I don't know if you want to, this is anthropomorphizing, of course, but that are kind of unrelated to our own goals, even if they're not like in opposition to those goals?
Yeah, great question. And so when I talked about thinking like humans but faster versus thinking at a qualitatively higher level, like these are really two different hypotheses about what could happen, right? So it could be that human thought is basically Turing complete, right? You can imagine maybe like the difference between humans and monkeys is analogous to the difference between like Turing machines and push-down automata. But like once you get to Turing machines, then it's universal, and there won't be any kind of fundamental change when you change the computational architecture, right? And so that's one possible hypothesis about the space of possible levels of intelligence, right? So it could be that, you know, just like you can build faster and faster universal computers, you can build faster and faster versions of things that think basically like humans, right? But it also could be that AIs have the capability of like thinking about things that humans just have no conception of, right? Like the way that chimpanzees have no conception of quantum mechanics. And that would be sort of like an even more extreme version of superintelligence, because like we wouldn't even be able to like reason about like what sort of things the AGI is reasoning about.
Thanks.
Roger, sorry, Dan, you want to say some more on that?
No, I was just saying thank you.
Okay, all right, good, good. Roger, I had a question for you, but I wanted to just check, do you want to go on to the next part of your talk first, or?
I think I'll take this question.
Okay, all right, good. So I wanted to ask about whether there's tension between the first part, sort of thinking about AGI futures, and the scaling laws, in the sense that, you know, do you think that's the path, right? I mean, I think we hit the limits of the data we can make available to our computation systems probably sooner than we get to anything like superhuman intelligence. So just think about the fact that, yeah, we're training GPT-3, but we're training it on a very tiny sliver. It's massive, right? From one point of view, it's what, 500 billion or 500 trillion or something tokens, but it's still a tiny sliver. And humans don't learn on those size data sets. So in some ways, well, our intelligence had to figure out a way to learn a lot and do a lot without computing massive quantities of examples.
Yeah, it's a great point. And so it could be that current methods will just completely run out of steam because they'll be bottlenecked by sample efficiency, and there just won't be enough data in the world to train an artificial lawyer, things like that, right? Another possibility is that computation and data can kind of trade off against each other. So the more processing you do with a GPT-like architecture, the more sophisticated the representations will be, and the more the more abstract level at which it'll be able to do the pattern matching. So you can imagine, like, if you were to ask GPT-3 to solve Math Olympiad problems, like there's probably nothing written down in human history that is sufficiently similar to next year's Math Olympiad problems that GPT-3 would be able to solve the problem, right? But if you imagine you had an architecture that's sort of like a hybrid between GPT-3 and AlphaGo, and it's like doing a search procedure as it goes along and using what it learns from the search procedure to improve its representations, then maybe, you know, it'll be doing pattern matching at like a high enough level of abstraction that it'll be able to make use of problems it's seen before. Sort of like how the human IMO contestants might notice a problem and think like, you know, hey, I saw a problem just like this in like, you know, previous Olympiad, but that they noticed that after having like done a lot of work to transform the problem into different formats and things like that. So like that would be one hypothesis in which more computation would be able to solve the problems with sample efficiency, in which case you're scaling something like GPT-3 further could actually result in AGI.
Right, right. Okay, great, thanks. We'll go on to your next part.
Okay. So the second part of the talk will be on Mesa Optimization. And this refers to when an AI might find it advantageous to solve a problem by building another agent or another optimization procedure. And so here we have an AI researcher thinking, hey, my life would be so much easier if I built a robot or a software agent or whatever. But then maybe the robot is thinking the same thing, like, hey, my life would be so much easier if I built an agent. And so the idea is that an AGI might try to achieve its goals by creating another optimization process that has different goals that are somehow instrumentally useful. And so then that other agent or that other optimization process will be the one that's actually interacting with the world. And so we have to worry not just about the agent that we built directly, but the other ones that might emerge from this process. And this is something that could happen even if we design an AGI with a non-agent-like architecture, such as the comprehensive AI services proposal by Eric Drexler. And so this problem was pointed out by people at the Machine Intelligence Research Institute, or MIRI, and most of this argument comes from this paper by Hubinger et al., Risks from Learned Optimization in Advanced Machine Learning Systems. And so in a sense, mesa optimization is everywhere. So like one kind of human analogy is that planned economies don't seem to work very well. But if you're a government, what you can do instead is you could design the market incentives so that the individual agents who are optimizing their own selfish interests will be incentivized to contribute to the overall societal welfare. Evolution, to the extent that we can think of it as an optimizer, found that it was a good strategy to program animals to have various drives, things like feeding and reproduction, things like that. These drives, they might support genetic fitness, but they're not the same thing. And so humans don't go around trying to maximize the number of offspring. You can think of all sorts of things that we do that are at odds with the goal of genetic fitness. An example that might be familiar to AI researchers is generative adversarial networks. Basically, if you're trying to generate things that look like images, like we see on the right, a good strategy to do that is to train a discriminator network whose job it is to classify real versus fake images. Then you can try to fool the discriminator. And so even though your goal is to produce images, it's kind of instrumentally useful to build this discriminator network that has the different objective of classifying real versus fake. And so the reason that we should be worried about this from a safety perspective is that it seems likely that mesa optimization will be a good strategy for generalizing in the face of moderate distribution shifts, right? If you want to hire someone to do a task, you could give them a very detailed set of instructions, but you're probably better off giving them a high-level description of what you'd like them to achieve, and then they can figure out their own flexible way to solve it. So similarly, we might expect mesa optimization to be a good strategy that AI could adopt for solving its problems. But the problem is that when a mesa optimizer fails to generalize, then the failures might be more catastrophic, especially if the mesa optimizer is given lots and lots more resources than it was trained on. And so from the perspective of AI alignment, we can decompose out two aspects of the problem. There's the outer alignment problem of ensuring that the base optimizer's objectives are aligned with our own. So we normally think of as the AI alignment problem, but there's also the inner alignment problem, which is sort of like the outer alignment problem from the perspective of the AGI, right? How do we ensure that its mesa optimizers are aligned with its goals? And so here's some questions that deep learning might be able to inform. So can our current architectures represent mesa optimizers? Can we recognize when mesa optimization is happening? Is it actually advantageous? So we'd expect our architectures to use this as a strategy. And can mesa optimization fail to generalize under distribution shifts? And so what do I mean by whether networks can represent mesa optimizers? Well, let's say that we want to classify objects in images, but the images are blurry because the camera person couldn't hold their hand steady. And we train a neural net, just like ordinary neural net architecture, to solve this problem. We don't tell it to use mesa optimization, but one possible strategy that it could use is to first implement an image deblurring algorithm and then to classify the resulting image. And so what I mean by image deblurring is on the right, in the top right, we have an example of an image that has a blur or camera shake artifact. But you can decompose it into an estimate of the clean image on the bottom, as well as the blur kernel, which is shown in the top left of that image. So that the blur kernel convolved with the image on the bottom should approximately give the one on the top. And so you can formulate deblurring as an optimization algorithm where you try to find an image that looks like an image, but also when you pass it through the blur kernel, you get the observed image. So this deblurring problem would be an example of a Mesa optimization objective, right? It's not the same thing as the classification objective, but it's something that would be instrumentally useful for it. And so this approach is one strategy that the neural net could take to solve this problem. Right? It might not just do it, it could solve it some other way, but this is one strategy that's available to it. And so will it do this? What would it take for it to learn an optimizer? Well, probably the vanilla optimizer in deep learning is gradient descent. So you're trying to minimize a function and you repeatedly take steps in the downhill direction until you've converged to a local minimum. So that can be written down with a very simple mathematical formula. And so can neural nets represent gradient descent? Well, there's a fairly uninteresting sense in which the answer is yes, because neural nets are universal function approximators. The result of running gradient descent is a mathematical function. And so even simple feed-forward networks ought to be able to represent it. But that's not a very interesting answer because the network might have to be extremely large and it's not a very natural thing for it to represent. So what are the architectural features that we might use, or like what architectural features would make it easier to represent gradient descent? Well, on one hand, gradient descent involves repeatedly applying the same update rule. And so we can encourage that by having a recurrent architecture. Right? Recurrent means that the units kind of feed into themselves. Or equivalently, we can impose weight sharing between different time steps. Right? So the weights of the architecture applied in one time step are the same as the weights applied in a different time step. Another feature of gradient descent is that we repeatedly retrieve the previously stored value and then update it. And so we want an architecture that's good at retrieving and updating previously computed values. This is something that LSTM architectures and residual networks are very good at. And finally, gradient descent runs a procedure repeatedly until it converges to a fixed point. And this is another feature that can be built into neural net architectures. And so none of these things were specifically designed in order to do Mesa optimization. They're just features that turned out to be really useful in other contexts. But because these are pretty standard motifs of neural net architectures, it's pretty likely that our networks are well positioned to support Mesa optimization. And even though this isn't done very often, it's also well within our abilities to just unroll the entire optimization procedure and treat that like a neural net and train it with backpropagation in the ordinary way. And so this was done by David Duveneau in a 2015 paper, the one that introduced the AutoGrad framework. And this is also the inspiration for other techniques like the MAML algorithm. So we have architectures that are very good at representing things that are essentially optimizers. All right, so if Mesa optimization is possible, will we be able to recognize it when it happens? And if so, maybe we can just outlaw it. We can design our architectures so they can't represent Mesa optimizers. But this is probably too big a constraint. The reason is it's just very hard to look at a dynamical system and tell if it's optimizing something. So you can consider, for instance, heavy ball momentum, which is one of the main optimization algorithms we use for training neural networks. Heavy ball momentum is basically a discretization of Hamiltonian dynamics. And so if you want to ban heavy ball momentum, you essentially have to ban your architecture from simulating physical systems. That seems like a very big constraint. Is Mesa optimization advantageous for the network? Right? Will it help it to solve problems that it wouldn't be able to solve otherwise? And I'm not sure that anyone's looked into this exact question, but we can ask if the sorts of features identified that make neural nets better at representing Mesa optimizers, like do these features also improve generalization? And so here we have two papers looking at particular architectural motifs that support Mesa optimization. On the left, we have recurrence. On the right, we have the ability to iterate until you reach a fixed point. So the figure on the right was actually work I was involved with, done by my students Kai-Chu Liang and Gemma Neal. And what we're looking at here is basically upwards generalization. So you have a task that's parameterized by some difficulty parameter. So if you're classifying blurry images, it could be the amount of blur in the image. And so upward generalization refers to generalizing from easier instances of the problem on the training set to harder instances on the test set. So what we have on the right is basically a couple different tasks where we're testing upwards generalization. The x-axis corresponds to the difficulty parameter, and everything to the left of the dashed line represents the training distribution. So the blue curve is the one that explicitly tries to do fixed point iterations, and the orange curve is the more traditional neural net architecture that just runs for a fixed number of iterations. So the blue one seems to generalize much better to more difficult problem instances. And finally, if we implement an architecture that does Mesa optimization, then might it fail to generalize under distribution shifts? And this relates to a very big topic in deep learning research these days, which is implicit regularization. And so basically the idea is that for a lot of machine learning problems, like most neural net training these days, there are often many different solutions that minimize the training objective. So there might be very different functions that the neural net can represent that all fit the training set. And which one it chooses just comes down to which one it finds first, right? Which one is easier to find with gradient descent. So this is a kind of implicit regularization to contrast it with situations where we explicitly impose a regularizer on the model. And so the cases we're most familiar with in machine learning are the ones where implicit regularization is beneficial. So here's an example of a regression task. We're given a regression data set that we see on the left, and we fit a degree 6 polynomial to it. And gradient descent winds up learning this function that we see in the middle. But it could learn a different function, right? So the one on the right is a perfectly valid solution. It also fits the data set perfectly. But the one in the middle is easier for gradient descent to find. And so gradient descent seems to be imposing some sort of smoothness assumption, which is often a good assumption for doing regression. And so this implicit regularization effect is a big part of why deep learning actually works. But what's easy for gradient descent to find isn't always what makes the most sense, or it's not always what is intuitive to us. So here's an example of data set distillation. By the way, this example was done by my student, Paul Bicol. So in data set distillation, we're trying to summarize the data set into a smaller data set, such that a model trained on the distilled data set will do just as well as one trained on the full data set. And so we have the base objective of maximizing the performance on the original data set, and the Mesa objective is to maximize the performance on the distilled data set. And so basically, the algorithm is trying to adjust the locations of the distilled points in order that the Mesa optimizer will perform as well as possible on the original data. So this is what a good solution might look like. Right? So we can summarize the blue data set into the red one, which has a much smaller number of training examples, but pretty much perfectly outlines the function. What happens if you actually run gradient descent on this? This is pretty surprising. right? So even though we're making it very easy for it by giving it 100 points to work with, it still doesn't really make use of them, right? It essentially just keeps the points in the few clusters, and that is enough for it to optimize the outer objective, right? So because we're giving it a polynomial regression model, these clusters of data are enough to solve the original problem, but the solution isn't going to generalize, right? If we replace the polynomial regression with a neural net or something like that, then it's going to make crazy predictions. So this is the sort of thing that we actually have the conceptual tools now in deep learning to analyze. And so we can actually use the sorts of techniques that have been developed in supervised learning to explain in much more detail why this happens. And so in terms of what deep learning can contribute to understanding Mesa optimization, well, how do we recognize if a neural net is implementing a Mesa optimizer? Under what conditions is it likely to happen? Does it depend on the network architecture? Does it depend on the distribution of training data or the nature of the training tasks? If it implements a Mesa optimizer, does it display any sort of agent-like behavior that we should be worried about? How can we constrain a neural net architecture not to produce a Mesa optimizer, or at least can we constrain the properties of Mesa optimizers that it might produce? If it is learning a Mesa optimizer, how can we regularize it to perform well even under distribution shift? So these are questions that I hope that deep learning will be able to address. So I'll open it up now for the final discussion.
Great, thanks, Roger. Should we, let's see, why don't we turn off the, okay. We have a question from Mohammed.
Hello.
Yes. Oh, I'm hearing an echo.
Hi, with my advisor, Nicola. So we call me Echo. So my question was, right now we have like tools such as CDXPy layers, which actually lets you implement a optimization problem as a layer of your architecture. So explicitly having that. So what do you think about that? Since that is possible, like we explicitly are doing that, is it enough proof that that's actually possible? Like given a particular network architecture part of it would be effectively doing this Mesa optimization.
Yeah, I mean, I don't think that bi-level optimization is something we should be directly concerned about, because we're giving it a lot of information about exactly what the inner optimization problem would look like. It's something that we kind of explicitly put in there. So the kind of situation that's more worrying is when it just spontaneously decides to optimize something without us knowing what that might be. But I think that analyzing the behavior of bi-level optimization can tell us a lot about how Mesa optimizers might behave. Right. So, and actually, the last example I gave in this talk was sort of an example of that. This dataset distillation problem was an example of a bi-level optimization problem. And so, like when the outer optimizer is tuning the parameters of the inner objective, there are like many different solutions it could come up with, but some of them are easier to find than others with gradient descent, even if those aren't the most natural solutions or the ones that will generalize the best. So I think that, yeah, we can learn a lot from those sorts of architectures.
Thank you.
Beatrice.
Thank you so much for this talk. It was very interesting. I think my question might be kind of one of the open questions, because I have a question about the political implications of this, right? Like, how is this going to affect politics? Like, what actions can politics take? How do we regulate this? What do we even mean by going against our interest? And the other connected question I had to this was, I found the part about forecasting very interesting, because it's so related to climate change, but also other types of policies like pension reform, right? Especially when we don't know also like people's discount rates. Like, how do we know if people don't care about this and they have a super high discount rate so that they don't want to take any action now because they really discount the future in this, like, how do we make sure that something happens, especially if we don't even know that what the timeline really is, right? And there is that uncertainty.
Mm-hmm. Yeah, definitely great questions. And there are like a lot of issues around the political implications that I don't really know how to address. I mean, there's the scary question of international arms races. So if we believe that hard takeoff is possible, then like even if we were to solve the alignment problem, then we still have the problem that the one country or one group could get a huge first mover advantage. And so if it's countries, it could be a military advantage. You could imagine maybe like a company that develops AGI first will be able to sort of take over like many different industries. And so and arms races are kind of dangerous because from an alignment perspective, any of these actors could be incentivized to sacrifice safety in the interest of speed. Just like how with the Manhattan Project, they were willing to take sort of a non-trivial chance of like igniting the atmosphere and things like that because it was so important to defeat Hitler. So, so I think there are a lot of really complicated political issues involved with that. And how do we sort of maintain international cooperation around AI efforts, or how do we have kind of enough ability to monitor each other that we don't have these unstable arms race scenarios. There's an excellent report about 5 years ago titled AI National Security, commissioned by Jason Matheny. And they actually compared AI against other military technologies. I think they looked at like stealth planes and nuclear weapons and biotech, maybe a few other things. And like AI just seemed to be like particularly risky on like many different axes in terms of like being really hard to like monitor and being sort of cheaply available to sort of like non-nation actors and things like that. So yeah, definitely a big concern. So what was the second question again?
Sorry, that was about the forecasting part and like different discount rates that people might have, which also relates to issues like climate change and other types of reforms that are going to have benefits in the future, but immediate costs. And I was wondering if, there was any study into this specific issue and people's discount rates.
Yeah, it's an interesting question. I mean, I guess it is hard to achieve international coordination on things like climate change. On the other hand, like efforts to combat climate change are sort of an almost unprecedented amount of international cooperation resulting from scientific considerations. So it's like, in a sense, impressive that we've been able to achieve the level that we already have. And I think there could be sort of an implicit problem here that, as you say, people have different discount factors. So maybe we don't care about people living 100 years from now as much as maybe we should. On the other hand, I think the kind of amount of effort that is put into AI alignment today is pretty small, even by those standards. So I forget who made this argument originally, but there's this argument that if we found out that there was an alien spaceship en route to Earth, and it was going to arrive here in 80 years, and they had much more advanced technology than we do, we'd be pretty worried about that. Like, we're going to start preparing for that now, right? But if we believe that AI is like potentially 20 years away, potentially 80 years away, then it just feels like there's like maybe so much uncertainty, like what can we do now? And this feels kind of inconsistent.
Right. Yeah, I've heard that argument too, and I can't remember who it is. Maybe somebody will know, the alien spaceship on its way. Tegan.
Sorry, thanks. I remembered who that idea is due to, and then I just forgot. I'm sorry. I hope I remember it by the time I finish my question. I actually sort of have two questions, but I'll just ask one and then give somebody else a chance and then ask another. The first one is sort of more of a combination comment and shameless plug and also a question. I think it was the second section of this section, you mentioned banning Mesa optimizers and how like basically we can't do that because that would be essentially banning optimization or physical constraints or like hugely broad classes of algorithms. But basically I want to say, I think in general, sure, we can't ban it, but for a lot of specific use cases and maybe huge swaths of use cases that are really important, I think we can, and it's already starting to happen. And the shameless plug part is some work that I've done developing with David Kruger, who's now at Cambridge, on unit tests for incentives to cause distributional shift. And I'm pretty optimistic about this kind of approach in content recommendation specifically. So like online, use news feeds or like Facebook feed, that kind of thing. The EU has already banned user manipulation in those contexts, although what that means in practice, nobody knows yet. But if that kind of ban in policy holds and policymakers are looking for ways to ensure that, I think one way to do that would be to ban Mesa optimization in content recommendation. And I think we have sort of some starts on ways to do that practice.
Right. I mean, I guess when I talked about banning, I wasn't even like thinking at a political level. I was thinking like, if we were trying to like put constraints into the algorithm that prevent it from doing Mesa optimization, like let's say we wanted to do that, right? That I don't see how we'd even be able to draw that line.
Yeah.
And so like if we were to try to like prevent Mesa optimization from arising, that would mean, for instance, that if your neural net is trying to classify blurry images, then like it wouldn't be allowed to try to reconstruct a clean image by inverting the blur kernel, right? That would be an optimization problem.
I guess what I mean, to be more specific, is that sure, we can't ban Mesa optimization in general, but we could maybe successfully ban particular Mesa objectives. Or prevent, like strongly discourage them.
Right, we could, hypothetically ban people from directly implementing the Mesa objectives. Very hypothetically, you could say you're not allowed to implement a bi-level optimization routine that has the following inner objective, right? But this wouldn't prevent the network from, on its own, deciding to solve a problem by implementing an optimizer.
Right, but if we can identify the objective, sort of like making algorithms fairness blind, or like group blind, we could discourage the Mesa optimizer, like basically make it difficult to find the solutions that we don't want for particular cases.
Let's see. So, like what would the actual rule be? Like what if you were the dictator, like what sort of rule would you impose that would prevent people from writing algorithms that would have those optimizers?
Not broadly. That's what I agree with you. We couldn't like prevent Mesa optimization from happening in general, but with explicit regularization, for instance, I can imagine we could achieve not having a Mesa optimizer for particular Mesa objectives in practice. And the specific example I gave was achieving performance via causing distributional shift. That's one that we have a unit test for if an algorithm does that. So you could put our unit test as a component of an optimizer and at like the higher level optimizer, and that would discourage the inner optimizer from like arising.
Interesting.
can I jump in here? So I'm just trying to translate. So what the Mesa optimization, why is that changing our AI safety problem? What is the, I mean, if you're going to talk about banning it, and I'm thinking, okay, so in what sense is this contributing to the alignment problem, in the sense that you might say, okay, we don't want this kind of optimizer to arise? It doesn't, I mean, especially because, as you know, there's lots of cases where, in fact, we achieve lots of objectives by creating these other, like, you know, you talked about, you know, markets or biology and biological drives that kind of, you know, by optimizing that drive, you actually optimize the ultimate objective. So I'm trying to think, why is this a consideration for AI safety in particular in alignment? Why is it changing the problem? Is it that it's more complex? Is it that it's like, is it because of explainability? Like, we knew what objective we originally gave it, and then turns out, you know, the system has invented something else, and it's hard for us to observe that. Is that, yeah, so I'm just wondering how you see this as an important topic for something we really need to think about from an AI safety point of view.
Yeah, I mean, I guess the sort of long-term safety consideration would be like, maybe you have an AI whose values you've successfully aligned with ours. So it's like, it understands human values really well and is motivated to achieve them. And it realizes that money would be very instrumentally useful for achieving our objectives. And so it goes off and implements another agent whose terminal objective is to make as much money as possible. And then that agent maybe doesn't have the safety properties. And so it you know, acquires more resources and turns the world into dollar bills, right? And it's hard to see like what sort of safety properties you can put on the outer system that will guarantee that there wouldn't be some kind of inner system that arises that has like different objectives and it doesn't have whatever safety properties we put on the outer one.
Okay, I mean, I guess I sort of see that. That's how I understand the alignment problem in general is, right? Okay, if you say cure cancer, the system may say, well, I got a way to cure cancer, we'll kill everybody, then nobody gets cancer, right? And that's that. I think of that as just, that's the alignment problem, right? That you could get solutions in that way. So I'm not sure what the addition of the idea that there's this Mesa optimization layer, what that adds. And I think I am just missing it. So I'm just trying to understand what it's adding.
Yeah, I mean, I guess it's yeah, it's a subtle distinction. And I guess in that example, you could have an agent, right? So like a failure where it you know, cures cancer by like blotting out the sun would be like something where it, I guess, misunderstood our objectives, right? It takes actions that maybe it mistakenly thinks would be, you know, beneficial to our goals. Whereas the sort of picture we have in mind in Mesa optimization is that it sort of correctly understands what we desire from curing cancer, but it decides a good way to do that would be to build another agent that has objectives that are instrumentally useful to it, like acquiring as much money as possible. And then like that agent becomes really powerful and you know, works contrary to the outer one's objectives.
So if we were going to translate this to the principal agent framework, it's, you know, where the principles, we create the AGI agent, that agent also becomes a principal with respect to that, to the other agents. And if we haven't thought through the dimensions of how do we constrain the capacity for the agent to become a principal in another relationship, that
right, exactly,
lost control there. Okay.
Right. And I guess in principle, like, you know, if it's smart enough, then it would probably, you know, solve the AI alignment problem itself and like make sure that whatever agents it creates are aligned with it.
Right.
So I guess the worry might be if it's like, you know, not smart enough to do that, but it's like smart enough to implement another agent. then it could cause a catastrophic problem for that reason.
Oh, I see an impossibility proof in here somewhere. Yes. Yes. Okay. Great. Let's go to Jack, and then Avery.
Hi again. I put in the chat I think an example that might be a kind of intuitive version of an answer to the question that was just asked, which is when a police officer uses racial profiling. They are using a Mesa Optimization thing, which is totally at odds. They might correctly understand the goals of public safety, but they've instituted a racial profiling sub-algorithm, which is totally at odds with those goals. And people worry about sentencing algorithms sort of implicitly developing racial models and stuff like that. So that might be I'm not sure if that's the same kind of thing you're talking about. So I guess that's a question, but the question I actually wanted to ask was on I really liked the slide you had with the polynomial and the distilled data set. I thought it was a really evocative example, but I think I was missing a part of the argument there, or didn't understand, because in that case, your distilled data set ends up being, however many data points you asked for, right? But they're basically in clumps, and they're in, n clumps because it's an nth degree polynomial, right? So in that case, like, it's supposed to be an example of Mesa optimization failing, but because you have like a polynomial finding algorithm and the data set it's given is in fact an nth degree polynomial, it's not obvious to me that that would generalize to other contexts where you have more complex AI on looking at more complex data.
Yeah, I mean, we certainly shouldn't treat that example as definitive proof of anything. I think it's like a nice intuitive example that probably has some things in common with what we'd be worried about in Mesa optimization. It's like not even exactly Mesa optimization in the sense that we explicitly implemented this bi-level programming formulation that was like, explicitly telling it that there should be something optimized in the inner loop. And so I guess my reasoning is that the kind of dynamics that happen in that situation might still happen in a situation where it decides on its own to implement a Mesa optimizer. So like maybe you have just a really general architecture in the outer loop, but it decides that a useful way to solve a problem would be to create a distilled data set, right? And so then the kind of generalization failure would arise because it solved for the distilled data set with one particular learning algorithm in the inner loop, and the data set was enough to convey the correct function to that particular algorithm, but it wouldn't work if you replace that algorithm with like a neural net or a GP or something like that. So it's sort of somehow overfit to the particular algorithm used for the inner optimization.
I see.
That's what I was trying to get at with that. Yeah.
Avery, your hand went down. Did you still have a question?
Yeah, sure.
Okay.
So at the beginning of the talk, you were using Bostrom and you said AGI will know it when we see it. And then in the second part of the talk, you moved to Mesa optimization. We probably won't know it when we see it, right? And I just wanted to ask you, just so I can understand some of the comparisons, where does Trump fit in here? Because is Trump a sort of Mesa optimization of representative democracy based on imperial Rome and a bad faith imitation of Republican Rome? Or is Trump AGI? And just trying to understand the, perhaps with respect to climate change, right? Would a Mesa optimization of the climate change problem be something like the oxygen die-off with the evolution of photosynthesis? Or what are you trying to point to, a kind of emergent property from AI that can't be controlled and that will come about through Mesa optimization? Or do you want us to think about how Mesa optimization will lead to something at a larger scale that can be forecasted and tracked? I don't know if I'm following the way that you're putting this together. So tell me if I'm totally missing something.
Yeah, I mean, I wasn't intending the two parts of the talk to like fit together quite that tightly. You can think of them as like two different ways in which I think deep learning research can clarify some aspects of AI alignment. So, I mean, I wasn't trying to take the Trump analogy very far. Like that was just sort of the, a very specific point about not always being easy to put a scalar value on intelligence. That doesn't mean that it wouldn't prevent an AI from becoming very powerful. In terms of like with superintelligence, I guess you'd know it when you see it, or at least like if it chooses to like act in the world, then we know it when we see it. It might decide to stay hidden for a while. Mesa optimization, it doesn't necessarily require human level intelligence, right? It's the sort of thing that can arise to some extent even in today's systems. The version of it that we'd be worried about would be if the inner optimizer sort of has agent-like behaviors, or it'd be incentivized to do things like preserve its own goals and acquire resources and things like that, right? Like at some level of sophistication, the inner optimizer might develop the same sorts of convergent instrumental goals that I outlined at the beginning of the talk. It'd be like hopefully a long time before we have to worry about any of that, but we might as well get started now on understanding sort of conceptually what happens.
Great. Thanks, Roger. Thanks, Avery. And a last quick question from Francois.
Yeah, so you were talking at one point with that alien spaceship analogy, how if we knew aliens were coming, everybody would sort of jump on solving that. And so in AI alignment, we just don't have that sense of urgency. And so my initial thought then was like, okay, well, everybody in AI should just move towards AI safety. But then part of your talk today highlighted how work that's been done independently of AI safety, just developing deep learning, can help us sort of shape the problem of AI alignment, or gives us more insight than if we were just fumbling in the dark. So I guess from a policy point of view, like if you were the dictator and you could say, this is the proportion of researchers that should work on safety versus other aspects of AI, what would you pick?
Yeah, it's a really tough question. I mean, I think right now, with such a small percentage of the overall AI effort is going to safety, that should be much higher than it is now. It seems hard to put like precise numbers on how it should be.
That's a great good place to end in terms of how much we should be spending time on this. I think more than we are. How's that? More than we are. X plus something. Thank you so much, Roger. That was a terrific talk and a great way to kick off our series this semester. And thank you all for joining us. Next week, we have a talk by visiting scholar Avinash Kalas, who's going to be talking on quantifying the user value of social media data, and I hope I'll see you all then. Thanks a lot.